can
Hello.
hear you.
Hey, so first of all, I will not take more than 5 minutes. I would really like to thank the AFLOW collaboration, particularly my good former classmate from a long, long, long time ago, and my good friend Stefano Curtarolo. Since a couple of years ago, he has been asking me if I would be cool for them to offer a school like this. And last summer it was we were too busy, and we couldn't make it happen. And this summer, we just made it happen, very quickly, thanks in great part to Lisa Perez from the Texas A&M High Performance Research Computing Facility. She did a lot of the logistics for this to happen. But most importantly, I think that this is definitely this was made possible by Stefano and all his group of great researchers, postdocs, staff scientists at Duke. And I cannot thank them enough for the dedication and for all the time that they are committing to offering this school. This is a one-of-a-kind school, and we're really happy to host it as part of our computational material science summer school as a satellite school. And I hope that this is the first AFLOW school that we offer. I will not take more time from the introduction. Thank you, Corey, and thank you everybody from AFLOW for putting this together. And again, thank you to Dr. Lisa Perez for all her work in making sure that the logistics just work through. Okay, thank you guys.
Thank you, Professor Arróyave. Okay, so we will get started now with the introduction. It's going to be led by Cormac Toher. Yeah, I'll pass it over to Cormac now.
Okay, thanks, Corey. Share my screen. So everybody can see my slides? Okay. So today I'm going to give a quick introduction to the AFLOW integrated infrastructure for computational materials discovery. So this will give you just first I'll give a brief overview of the logistics of how this school will work. I'll introduce the various instructors who will be helping out in this school, and then I'll talk a little bit, give some motivation behind why we developed this code and why we perform these types of calculations. Okay, so first I'll just introduce the team. So my name is Cormac Toher. I'm a research professor at the Center for Autonomous Materials Design at Duke University, who's just led by Professor Curtarolo over here. Then I'm joined here by Dr. Corey Ozis, a postdoc in our group, Dr. David Hicks, who's also a postdoc, Dr. Marco Esters, and Dr. Rico Friedrich. So we'll be hosting us five will be hosting various sessions throughout this workshop. So we'll be leading different sessions, and we'll also be helping with the various tutorials, so the various exercises. We'll be dividing up into breakout rooms. I'll talk about this a bit more detail in a few minutes. Okay, so first of all, as Corey mentioned, your microphone should be muted. So everybody's microphone should be muted automatically, and you will need permission to unmute. So if you do have a question, you can either use the chat function to send a message, and in particular, if you have technical difficulties, you should see there should be a user in the participants menu called support, so you can send a message to them if you have any technical issues, or you can raise your hand. So to raise your hand, again, you will hit this participants button. You would go over here, then you would hit. So this is the participants button. This will bring up this participant screen you see here on the right, and then you hit the raise hand button, and then you will see here this blue dot. This blue hand will be raised. So if you do this, then one of the meeting host will see this, and they can check if you have a question. They can unmute your microphone so that you can actually talk to us. And this will probably be more common during the actual breakout sessions when there'll only be smaller groups, and then we can interact and explain things in more detail, and we can answer questions. Okay. So then, as I said, we have these breakout sessions. So in each one of these sessions, each one of these different classes, there will be exercise sessions. So it'll be basically tasks you have to do so you can learn how to use the code. For these sessions, your group will be separated into these breakout rooms. So there'll be about 10 participants in each breakout room and one instructor. So then you can ask the instructor for assistance. You can share your screen with them. You can ask, say, if you're having any problems, and they can explain things in more detail. And exercises, materials, they're available on this TAMU open, so this Texas A&M University open on-demand portal. So you should have already received some instructions on this. But the instructional video is here. So if you go to this site, you can see the video. You can see how to log in, how to open up open up one of these portals so that you can actually start performing the exercises. And the exercise materials are also available. If you go into the desktop folder /AFLOW day 1, day 2, day 3, you'll see different things like example scripts, some already pre-calculated things that you can then do post-processing on, etc. Okay, so when you go into this on-demand portal, so hopefully some of you have already tried this, but you can basically use this button to launch a Vidi desktop. Then once you do that, you'll have an option for the number of hours. So I recommend setting something like 10 or 12. So you only have to do one for the day, and you can then do a 4 cores. So keep the number, try not to do too many cores, otherwise you might have to wait a while for it to start up. Then you can hit this button. This will launch the desktop, and you will see, and so then you'll actually see these basically just like a computer terminal window. You also have this option to share your desktop. So you can share view only. So if you're having questions, if you're having problems, you can share this with the instructor inside your breakout room, and then they can see what you're doing wrong. Okay, so once you open up this portal session, you'll see it's basically just like a computer desktop screen. If you go into applications and then system tools and then down to terminal, this will allow you to open up a terminal window, which will be useful for if you want to run commands. So here's an example of a terminal window that's opened up, and you can see that we've switched into the exercises for day 1. And then the other thing we'll need to do is you need to load this module. So module load AFLOW/T, and this will load up things like the various, it will load AFLOW so that you can actually run the AFLOW command. It will load up various other libraries that you'll need to run the workshop. And you will also have access to VASP if you load this. So this is the DFT code that Corey is going to talk about in the next session. Okay, one other thing that's important, that's a little bit tricky here, is if you want to do copying and pasting inside this terminal, you'll have to open a special clipboard. So if you look here on the left-hand side, you have this button. So if you open this up, you'll see, and then you click on this button here, you can then open up a clipboard and you can start copying and pasting things into this clipboard, and then from the clipboard into a text editor. And you have various different options of text editors. If you're not familiar with text editors, if you're not familiar already with, for example, VI, then I would suggest to use gedit, so G-E-D-I-T, as your text editor. It's something that's relatively intuitive, very simple to use. Okay, so that's the logistics part of the workshop out of the way. So now I want to talk a bit more about motivation, about why we actually do this type of materials design, what we're actually looking for. So first of all, when we're doing material science, we're motivated by applications. We're trying to find materials for specific commercial, industrial applications. So here's an example would be, for example, for if you want to find thermal barrier coatings to put on inside jet engines. So especially this is very important for the turbine blades inside the jet engines. These are exposed to extreme environments, so very high temperatures, corrosive exhaust gases. So you need to have something that will coat them to protect them both from the chemical attack, from the exhaust gases, but also from the high temperatures. So you want something that, for example, might have very low thermal conductivity, very high melting temperature, and so on. And it's also chemically unreactive. So that would be one example of a type of material I might be looking for, advanced material. Other examples would be super hard wear-resistant coatings. For example, for coating drill bits, for oil drilling, or just normal drills, or for coating machine tools, cutting tools, etc. Another example might be if you were looking to look for materials for medical implants. So for example, bone screws, you might have something that you want not to corrode inside the body. You might want something that will actually eventually dissolve inside the body, but you want to be able to control the exact rate at which it dissolves because you don't want it to go too fast or too slow. So then you're trying to look at just the corrosion resistance of the material to use for these medical implants. And you also it's also very important for these materials that you control the mechanical properties as well, because you want them to match the bone. Otherwise, you can have issues with things like stress shielding. Another example would be more for energy harvesting, for example, for photovoltaic materials. Then for energy storage, you're looking for materials like solid-state electrolytes for lithium-ion batteries. And then other more advanced exotic materials might be things like superconductors, or you might be looking, for example, for heat sinks for advanced electronics, so things that keep the microchips cool. Okay, so then to get an idea of the challenge, the size of this challenge, here I've shown the periodic table. So basically all the elements up to bismuth, so basically all the non-radioactive elements, excluding the noble gases. We have about 78 of these elements. If we look at all the ways we can combine these elements just in pairs, we have about 3,000 of those. For ternary, so if you combine just three different elements, you can make 76,000. 4, you get over 1 million. 5, you get 20 million. And by the time you go up to 6 elements, you can have 250 million calculations. And that's not even considering different stoichiometric ratios, not considering different types of structures. If we start considering, for example, what we call these prototype structures, so David will be talking about this a bit more tomorrow. These are different types of basically geometric arrangements of the atoms. And if you consider all the different ones that we've already discovered within the AFLOW database, and we consider all the different possible elemental combinations that we can use to decorate these different structures, we get something like of the order of 10 to the power of 177 different materials. So this is an enormous number of materials. And this is obviously not something that can be done by hand, either whether it's by computationally, so you're trying to creating all these structures by hand, or something you can do even in the lab experimentally. And so because of this, we have to try and explore, at least trying to start exploring this huge material space. This is why we've developed this AFLOW, so this automated materials discovery framework. So basically the way we start from experimental, either from two main routes. We either start from already observed experimental structures where we're just calculating the properties of known structures, of known materials, or we do what we call structural prototypes. And this is for discovering new materials. And David is going to talk a bit more about this in detail tomorrow morning. So we decorate these backbone structures with different elements. Then we perform density functional theory calculations. So this is basically at a quantum mechanics level. We calculate the properties of these, the energy, electronic structure, and so on. Then we pipe this data into this searchable and sortable database to try and store it so that we can actually do data analysis, we can collate data, etc. And then finally, we can either interrogate this database to find candidate materials for specific applications, or we can use things like to identify trends, train machine learning models, etc. Okay, so then the way that AFLOW works, we start from, it basically wraps around the density functional theory code. So from a single input file, this AFLOW.in file, and David will talk through about how this, the structure of this file this afternoon. You can start multiple different density functional theory calculations. So you can start calculations. So this is especially important if you're trying to calculate thermal or mechanical properties that we'll talk a bit more about on the last day, on Thursday. You then monitors these calculations. If you get an error, it can then automatically change some settings for the DFT code, rerun the calculation, and then try and solve the problem. Then once the calculation has, if the calculation is finished successfully, they'll parse the results of this file. It'll do things like plot the electronic band structure to it'll extract the electronic band gap. You can then combine multiple DFT calculations together to extract things like thermal properties, elastic properties, and so on. And then finally at the end, we pipe the results into a online database for online storage and dissemination. Okay, and the particular database we have is it's available at aflow.org. So here, if you go to this page, you'll see this. This is the main web page. You can get a breakdown of how much data we have. So now we have only 3.2 million materials entries. We have almost 600 million different materials properties in total. So this is total, basically property values. Then you can get a breakdown of the different amounts of types of materials we have. So for example, how many elastic properties we have, thermal properties, binary systems, binary entries, and so on. So if you scroll down, then you'll see this apps and docs part of the web page. So this is various online applications. So you can, for example, you have things like the machine learning application that I'll talk about on the last day. We have also things like the convex hull application that Corey is going to talk about tomorrow, and so on. And right now, just as an introduction and to get some warm-up exercises, I'm going to talk about this Mendelib search option. So this is basically an advanced search page. So you have different options here. You can basically select different elements. You can select groups of elements. So for example, if you want to look for alkali halides, then you can perform property filters. So for example, if you want to go into electronic properties, you can search for materials within a specific band gap range, or mechanical properties if you want to look for things like bulk modulus, etc. And then another thing that's very important here that's quite useful is this number of species button. For example, if you wanted to look just for sodium chloride, you will select sodium and chlorine, and then you should set the number of species equal to 2. So to show this example, here I've selected sodium and chlorine. Then I've also set the number of species equal to 2. So we only get sodium and chlorine and not everything else that contains sodium and chlorine. So for example, you might have sodium and chlorine and oxygen. So we eliminate these types of materials by just restricting the number of species to be 2. Then here I've added a filter for the electronic band gap. So you can also then select, if you hit this restrict value button, you can restrict band gaps in a particular range. So for example, if you wanted to see materials with a band gap between 3 and 6 electron volts. And then to add more filters, so to add this filter, you will actually go down here. So you select electronics, then you click on this add column button, and this will bring up the filter up here, and then you can adjust the settings. Okay, so now we're going to try the first set of exercises. So I'll just run through them first before we start breaking up into the breakout rooms. So the first exercise will be to use this advanced search functionality. So if you navigate to this page, this AFLOW.org page, and then go to the search page, to find the band gap for silicon carbide with the zinc blende structure. So this will be space group number 216. Then the second exercise is to use the advanced search functionality to find the bulk moduli for materials containing titanium in the AFLOW database and see how many results are returned. Then at the end, you would use the restrict value button to limit the search for only materials for which the bulk modulus has already been calculated. So you don't need to change the settings range. You'll just hit the restrict value button, and this will basically eliminate all the ones where the bulk modulus has not been calculated. So if you then use the sort function by just clicking at the very top of the, by clicking on the header containing the, at the top of the column with the bulk modulus in it, you can basically change the sorting. So you can sort in ascending or descending order of bulk modulus. So that way you can find the material with the highest bulk modulus. So then open up this page, the entry page, and check what the lattice type and space group of this material is, and find out whether it's a metal or an insulator. And also, just before we break up, as well as the AFLOW.org page, there's also this option to use this. There's an alternative server, which is the aflowlib.duke.edu page /search/UI. So if you go to this page, you will also see the same AFLOW web page. So just in case anybody has any problems accessing the AFLOW.org page, they can also use this page as well. Okay, so with that, I think we're going to, if we start breaking up into different breakout rooms, so we can start trying out this exercise. I think it's now it's just coming up to 10:25. So I think if we take maybe, let's say, until 10:35 to do this exercise, and then we'll come back, or sorry, 9:35 Texas time, to come back to this main room. Okay? Throughout these exercises so that everybody can see what we do, how we do it. Okay, so the first question is to use the advanced search functionality to find the band gap for silicon carbide in the zinc blende structure. So very quickly, if we go to the AFLOW page, we go to the Mendelib search option, we choose silicon and carbon, we set number of species to 2, we select crystal, so then we go down and we'll hit this one, so space group relax. We do restrict value, and we go from 216 to 216. So we only get the zinc blende structure. And then we select electronics, get the electronic band gap, and then we do a search. So in this case here, you can see that the electronic band gap is 1.37 electron volts. Okay. So then if we bring up the next question, we want to use the advanced search functionality to find the bulk moduli for materials containing titanium in the AFLOW database. So we do titanium. And then we want to do bulk modulus. So we look at mechanical. So first we close this one and close this one. We'll look for the, we'll do the VRH bulk modulus. Then we'll do it. We don't want to control number of species. So we hit search. So now we get 2,307. Now if we do the restrict value, now we can get the Iranian titanium. So here we do a sort by clicking on this one. Then we find the highest entry, which is iridium titanium. And then we can, if we try to, right. Try and zoom in a little bit. Okay, so here we can see this is the one with the highest bulk modulus. We scroll down, we can look at different properties. So here we can see the space group, it's number 221. So this is simple cubic. And if we scroll down to the very bottom, we can see electronic properties. So we can see the band structure here. You can see that there's no band gap, so this is a metal. And indeed, if we should see the electronic properties here somewhere. Anyway, okay, you can see it's metallic. Okay, so then if we move on, if we look at the stability screening, so now we have all this data, we want to find useful materials. So one of the first things we do is we try to screen for stability. So we both look for turbodynamic stability, where we calculate these, what we call this convex hull phase diagram, to find the ones that are actually going to be thermodynamically stable. And Corey is going to talk about this a bit more tomorrow, I think, about how we actually calculate these phase diagrams and find the ones that are energetically stable, and also predict things like decomposition paths. So if we try and mix some materials that are not stable, what they will decompose into. We can also check for things like mechanical stability. So here, for example, we have two different structures, two different polymorphs of titanium. So on the left, we have the hexagonal polymorph, which is the one that's stable at low temperature. And you can see here we have this regular phonon dispersion with no negative frequencies. On the right, though, we have the BCC structure, which is the high temperature structure. And you can see at zero temperature, you have this instabilities, where you have these negative frequencies. Then we can also use the data to do from design rule discovery. So here we have superconducting critical temperature. So here, for example, when we did a study on the entire database, we found that placing lead at this site tends to increase the critical temperature, whereas placing neodymium at this site tends to lower the critical temperature. Here's another example, which is on thermal conductivity and perovskites. So you can see here that so this is published in this paper here if you want to look it up for more details. So on the left, what we see is that for fluoride perovskites, the thermal conductivity tends to depend on the atom that's on the B site, whereas for oxide perovskites, it tends to depend on the atom that's on the A site. So then the third thing we can do, so as I showed you earlier, we have massive numbers of potential materials. To perform DFT calculations for all of these materials would be computationally very, very expensive. So instead what we do is we take the materials we've already calculated and we use that to train machine learning models to rapidly predict the properties of other materials. So I'm going to talk a bit more about this on Thursday evening, but here's an example of where we've trained a machine learning model. So we have a classification model to predict whether the material is a metal or an insulator. If it's a If it is an insulator, then we use a regression model to predict the bang gap. We've also used trained regression models to predict thermomechanical properties, things like bolt modulus, shear modulus, and so on. Okay, and now I'm going to pass over to Marco for a couple of minutes, and he's going to talk to you a bit more about how to install AFLOW.
Yes, good morning, everybody. Thank you, Cormac. AFLOW is not just a website and not just a database. There's also a lot of code and a lot of modules that you can use. So if you're interested in installing AFLOW on your own machine, you can do that on basically any platform that's out there. On Linux, even it's natively developed for Linux, but it also works on Mac, and it also works on Windows. Windows, you need additional software. There's some very neat subsystems that emulate Linux on Windows 10, and on other Windows versions, you can also use the Sequence software. And we have everything on the website. Cormac, if you can click the link to.
This one, not this one. Yeah.
Okay, thank you. So there are a couple of, it's basically a rundown on what you can do. For macOS, the instructions are fairly small, but Windows, we have a nice introduction about how to go about installing the Linux environment that you need. And if you have any questions or if anything goes wrong, you can always ask the forum. Installing AFLOW has been completely automated for Windows, Mac, and Linux. We just need a few preparatory steps. There's an installation script that you can use and just run, and it will install all the packages that you need and then AFLOW. But for any Linux user, this currently only works for apt-get, specifically for Ubuntu and Debian. These are the only systems I could test it yet. If I ever get around it for different systems, I will do that too. If there's any interest for me to, or for you to have that script work on other platforms, just ask in the forum or send me an email. Email addresses for all of us are going to be in one of the slides, I think, at the end. So if you have interest for me to develop the automatic installation script, for example, for Red Hat, for Yum, just let me know and I'll see what I can do. It also has the option to install all the Python packages that you need to run our Jupyter notebooks for the workshops, and also to run all the Python modules that we have. So everything is there. And if you go all the way down, you can even get the source code if you need to compile from the source because your system is not supported by the automatic system yet. If anything goes wrong, we have a forum. I think it's on the very top that you can click on and just ask where it shows the bug about the for the installation script, and we will make sure that we can get it fixed. Should be easy for everybody to install AFLOW on their own machines. That's all.
Okay.
Thank you, Cormac.
Okay, so then just to wrap up, I'll just go through briefly what the different sessions for different days are going to be like. So next session now in about 10 minutes. So we'll take a 10-minute break after this. But the first session will be an introduction to DFT and BAS by Corey. Then we'll have a break for lunch. And then in the afternoon, David will talk about how to use DFT with AFLOW, how to run DFT calculations using AFLOW and generate AFLOW.in files, etc. And then finally this evening, David will talk about the symmetry, how to do symmetry analysis with AFLOW. Then tomorrow morning, David will talk about structured prototypes. So this is something I mentioned a bit at the start of today. So we'll show how to generate hypothetical materials, how to decorate different structural prototypes with different elements. Then I'll talk about the database and the API. So how you can actually download the data programmatically if you want to download large data sets. Then this afternoon, on tomorrow afternoon, Corey and Rico will talk about thermodynamic stability. So we'll talk about how you generate these convex hulls and how to perform different types of corrections to formation entropies. And finally, on Thursday in the morning, Corey will talk about disorder, how to do substitutionally disordered materials. Then I'll talk about thermomechanical properties, how to calculate elastic properties and thermal properties with a bimodel. Then Marco on Thursday afternoon will talk about phonons, how to calculate phonon, like the kind of things I showed you for titanium just now. And then finally, on Thursday evening, I'll talk a little bit about the machine learning, especially the API, how you can access our machine learning models using just online. Okay, so thank you very much for your attention. And we'll break about a 7 or 8 minute break now before we start the next session with Corey.
Yeah, let's come back at 10 o'clock Texas time. All right, so in about 8 minutes. Thanks, guys.